Hi, I'm Rainer, and this week we're going to be doing a certain problem involving a block on a ramp. So in this problem we're going to have a block of mass m sitting on a ramp inclined at an angle of theta, and there's going to be a person pushing on it horizontally. And this ramp has friction with a known coefficients mu s and mu k. So we know mu s and mu k. And basically what we want to know is what is the minimum force we can push with that will keep this block from moving. Okay, so with that information we should start somewhere, and that's with a free body diagram. So let's make a free body diagram with our system being the block. So if I draw the forces, I know I have a weight force which points straight down, earth on the block. I know I've got a normal force, which is normal to the surface. And then I know I've got a friction force, and I know it's got to be static, because if it's kinetic, that means it's slipping, and we know we don't want it to slip. And I also know that if I take away the person's force, and I take away the friction, I know that this block's going to slide down. And so, really, what I want to happen is I want to push with as little here as I need to. And so I want the most help from static friction that I can get. So I want it to point up the ramp, because that helps me out with my force. So I know from the problem statement that this is going to be static and it's going to point upwards. And then finally, I have my sideward force right here. Force from U on the block. So with this in mind, we can move onwards. So let me draw some axes. I really like using tilted axes on this ramp because it keeps the acceleration all in one direction. And last, let's just sum some forces. So this is going to take a little more work than it seems. So if I sum the forces, let's start in my y direction. In the y direction, I've got the normal force pointing straight out, and that's positive. But then I've also got two forces that have components. So what I'm going to do is I'm going to draw a little ramp onto the background of this picture. I know that this angle right here is theta, because this is just the ramp that I've drawn on, and I know the friction points along the ramp and so on. And I know that right here I've got an angle that I'll call phi. And I know phi and theta, since they're members of this triangle, have to add up to 90. Well, I also know that if I draw a dotted line like this, then this angle right here makes a right angle with the entire thing. And so I have to say that this one's theta, because theta and phi now add up to this 90-degree angle. Okay, now keep in mind, I want to break both of these down into x and y components. So the weight force in the y component will look like this, and in the x component it will look like this. And so I can see from this that I want the adjacent side of weight. So I'm going to say minus the weight times the cosine of theta. Now in the same way, I know that this one is phi, and so I know I'm going to have to do the exact opposite. And so I'm going to go ahead and say minus f sine theta. We can do the exact same thing in the x direction. Sum the forces in the x, and it equals upwards static friction. And keep in mind, I said I wanted the most help from static friction I can get. And so in this case, I'm going to say, let's let static friction go to its maximum. So I'm going to say mu sub s times the normal force. Only because I want the most help I can get, right? And then I'm going to use very similar ideas with the angles to try to solve for the x components of these things, and I'm just going to get the exact opposite signs I got for the y direction, of course, or the exact opposite trig functions. So I'm going to say plus force from u is going up the ramp, so it's positive, and it will be times cosine of phi, cosine of theta. And similarly, well, no, in the x direction, right, I'm going to have a minus weight sine theta. And that's just this x component of the weight force. So let me think if I have everything. I have normal force, I'm sorry, not normal, friction force, U force, and weight force. This looks good. And if I want, I can say in the y direction, these sum up to 0 for mass times acceleration, ma(y), but since it's not moving in the y direction, I say this is 0. And as a result, I can find my normal force. Over here, I can say, I want this to be 0, because I don't want it to move. I know this is at its maximum value, these are all givens, and I can solve for f given this setup. So to do this, I solve for normal using the y equation, I plug it in here, and then I solve for f using the x equation. And that's all we need to do. The rest of it is taken care of in the fact that we use this maximum static friction force in this case. So that's all for this week. Thanks.